Hello, everybody. We're just going to keep rolling. Week 2, number 3, climbing stairs. It says dynamic programming here, so be scared. But really, dynamic programming is probably the toughest subject in the Elite Grind 75 list. Okay, climbing stairs. You're climbing a staircase. It takes n steps to reach the top. Okay, so door here. Each time, you can either climb 1 or 2 steps. And how many distinct ways can you climb to the top? So distinct ways can you climb to the top. Example 1, input n equals 2. Output is 2. There are 2 ways to climb to the top. You can do 1 step and then take another step, right? So take, let's say 1, 2, or, okay. So when I look at a problem like this, if I'm solving this from scratch, I try to think about what the tree looks like if I had to solve this brute force, right? So if you're given, let's say n equals 1. How do we get to 1? So the tree's here, we start, we take 1 step. There's actually only one way to get to 1 step because you can't take 2. Good to know. N equals 2. Well, for 2, you can take, the 2 here. You can take the 1. But if you take the 1, you cannot take a 2. Can you take a 2? No, because that would be 3, right? So here, that would be, what color should I make that? Green? Red? Or I could just delete it. So what about n equals 3? N equals 3, you still have the same decision. So here at this decision point, you're thinking about how to branch, right? So if the current, I guess, let's say, remaining CR, let's say, is less than 2, then we can only branch to 1. Else we can branch 1 and 2, right? Okay, so here, this is a 2. Now from 3, can it go 2? No, it can only go 1, right? So here, in this path, we have created 3, go 1 here. And actually, when you go 1 here, you can go back and go 2, right? You can also go 1 here, 2, no. Okay, so that's another pattern. I'm not exactly seeing the pattern yet, but let's keep going. So 2, 1. So actually, so 3. Okay, yeah, I think I'm getting it. So 3. Okay, so let's just do this side. So 2, 2. So this is new, right? And then 2, 1. You can't go 2 again, but you can go 1. So this is a 4 and this is a 4, right? Here's a 4 and here's a 4. And then here, when you do this 1, actually what's remaining is actually 3, right? So you can basically take this whole tree here, and if you did this, it'd be correct, right? Because at every point, what's remaining is that, actually at every point, what's remaining is a subtree from something you solved before. So if you look at this, n equals 5, you can go 2, you can go 1, right? Because you know it's large enough to handle these 2 cases. And then at this point, this is n equals 3, and this is n equals 4. You can actually take the entire subtree of n equals 4. Let's just color this and put that there. You can take the entire subtree of n equals 3, and let's make that green, and you can put this here, right? You can't really see it, but basically you can do this overlap, right? And here you're seeing that 2 plus 2 plus 1 equals 5. 2 plus 1 plus 2 equals 5. 2, 1, 1 equals 5. And then the blue one. So basically, what we're seeing is that it's all the combinations of n plus 3 and all the combinations of n equals 4, right? And that would be, what's this called? I'm just going to call it ways, right? So the ways of n equals 5 is the ways of this plus the ways of this, right? Or whatever the function is. It doesn't matter. I'm just going to call it function here. Okay, perfect. So it looks like that's that recursive relationship that we're looking for, because once you solve the smaller ones, then the larger ones are just a build-up of that. So, I mean, let's just think through what that means on the number line. So n equals 1, right, is 1. N equals 2 is 2. That's what we have here. N equals 3 should technically be this plus this, 1 plus 2. Right, so it's 1, 2, 3. Okay, so it is. It's 3. N equals 4 should technically be 3 plus 2. And it's 1, 2, 3, 4, 5. And it is, right? It's 2 plus this. So n equals 5 should be 8. Should be 5 plus 3, right? And we know that it's 8 because it is the branching of the function being called on 3 and the function being called on 2. So I guess we can just keep, adding this up until we get to the desired number of steps. So let's think about this in code, right? So we have all these. I'll clean it up because it looks a little ugly. Or at least a little messy, not ugly. My handwriting is never ugly. Okay, so let's just say current equals 1. Well, what's the function? The function takes n, right? The solution function takes n. And if n is 1, return 1. And if n is 2, return 2. And then just return the recursive function of n minus 2 plus the recursive function of n minus 1. I guess that would be it. And that would be linear space because of the recursive stack, right? The recursion stack will take space. So it's O of n space. And the runtime will be linear, right? Or the runtime will be n, so it scales with n. So the runtime is O of n, I believe, as well. Okay, well, it's possible that we run out of memory here if the number is large enough. So let's go ahead and code some of this. So we have climb stairs here, and if n is equal to 1, we're going to return 1. If n is equal to 2, we're going to return 2. And then we're going to return climb stairs n minus 2 plus climb stairs n minus 1. Let's run this and see how it performs. Climb stairs is not defined. Oh, because this is part of the solution. So we're going to have to make a method here. It's going to be called go. and we're going to return go and go. All right, let's try this, see if it works. Oh, it could be a none type. Interesting. Oh, obviously, because what if somebody passed? Actually, no, it's not obvious. Unsupported operand types plus for none and int. So at what point can, well, I guess somebody can do climb stairs equals 0, and then what would 0 be? If n is smaller than or equal to 0, just return 0. We want to handle the 0 case. This is what you always have to do. You definitely have to look and try to solve it in your head before you run the problem, which I did not do here, so I taught you poorly. So n is equal to 2 and the output is 1. So if n is equal to 2, oh, right. So because okay, you gotta slow down. Because I did the refactor and put something into Go, I still have this case where I'm returning these two. And that's what I'm definitely not supposed to do that, right? What I'm supposed to do is this. And I need to return Go with n. So let's just think through the cases. What if n was past the number 1? If n's past 1, then Go, it will be oh, I see. So I still have to do the check here. No. So if Go is past 1, it's returned 1. Oh, no, that totally works. If Go's past 0, it just returns 0. If Go's past 2, it just returns 2. And then if it's any larger, it's these two. So it's still this fundamental logic that I wrote here. I think the confusing part was having the Go function. So if you have to have a Go function, make sure that you call the Go function, like I'm doing on line 13. And then make sure that you have your base cases. But the time limit was exceeded for n to 44. Now, I could see what's happening. And this is it's kind of the exact thing I wanted to go through. What I'm doing here is not dynamic programming. I'm doing the case right here where you're iterating through every combination, right? And this is a really good learning experience for me. I'm doing it the slowest way possible. This is essentially the brute force way, right? Because nothing is memoized at all. So when I do n on a smaller number, like n equal to 1, n equal to 2, n equal to 3, 4, 5, 6, I have to run it again every time. So what I could do is I can possibly memoize the count, and I can say there's a memo here, and it's here, and if n is in the memo, return memo at n, and then also at any point before I do this calculation, this is a value. I want to return the value, but I also want to n at n store the value, right? So any other time, if it's in here, it's been memoized. So let's just print was memoed. Okay, so let's see if this is memoed, right? So I have a case here, I have a case 3, I have a case 2. Let's go let's go higher, right? Let's do 10. Okay, so let's just run it. So it should be memoed. I probably should have said what was being memoed. Okay. You gotta global that I. What's going on? Oh, or do you have to do non-global? Okay, let's get rid of this. Let's just get rid of this I. Wasn't ready to print that. Okay, so it was memoed 1, 2, 3, 4, 5, 6. So it's avoiding that calculation. And what's being printed? I guess that would be let's squid this. Okay, so what was memoed was 3, 4, 5, 6, 7, and 8. Perfect. This is perfect. Okay, so I'm going to go ahead and comment that out and submit here. And this should allow me to stop, basically to get to this point, right? So I beat 83% on runtime. Importantly, this actually becomes a way smaller problem, right? So once I calculate n equals 1, n equals 2, n equals 3 is easy. It's just the adding of 1 and 2. 4 is it's also easy. It's just the adding of 3 and 2. 5 is just the adding of n equals 4, n equals 3. So it becomes this linear process. All right, so I could have done this another way. I don't know if I have time to explore that one. Yeah, I did this in 17 minutes. Let's just go ahead and restart this. I could have done this another way now that I'm thinking about it. And I have this array here, right? And I basically, let's say go is a function. Make it pass. We're going to call go here. And I basically just have this array, right? So what I want is I want some code that does this part right here, right? Start the 1 off. Maybe start the 1 and the 2, right? So let's say the current so if I call go with n, last equals 1. So let's say prev equals 2 and prev equals 1, right? So let's say we have let's say we have a moving window. So it's not just this one, but let's say our moving window is these two, and I have perfect access to these two, right? So if let's just say if n is 1, I'm just going to return 1 here. If n equals 2, I'm going to return 2 here. Here at this point, I know that n is at least 3, right? So if n is at least 3, then I'm going to go ahead and say n equals n minus 2. So let's say n is 3, right? So let's say we have this one, and n is 3. Then if the remaining n, right, at this point, it would have been 3 minus 2, which is 1. So there's only 1 left. So if the remaining equals 1, then I want to return prev plus prev prev, right? I want to return 1 plus 2. But what if it was more, right? So what if let's say n is 1, 2, 3, 4. So if n is 4, then I want this 5, right? So prev is going to start here as this 1. Prev is going to start here as this 2. And it's going to be n. Let's walk through the 5. So it's going to be 5. N equals 5 minus 2, which equals 3, right? So n is 3. So n starts at 3. Prev is here. We're going to call go on it. If the remaining is 1, then I'm going to do that. Else, what I want to do is move prev, right? I want to move the idea of prev. So I'm going to say the new previous will be the previous, the prev plus the prev, right? But now, so what I'm doing is I want to move it. I want to move this to here, right? So I've calculated 3 in the new previous. Prev is actually now whatever is in the value that used to be prev, which is 2. And prev is this, new prev that I've calculated, right? So I'm moving this window, right? So here, n was 5, became 3, right? I've done this move now, and I'm going to return the remaining of n minus 1, right? So let's think back to it. So in the beginning, this was prev and this was prev. N was 5 minus 2 is 3. Because n is 3, it's not 1. I'm going to move this 1 step. The window is going to go up 1 step. And now n is going to be 2. Now, I should actually stop here. Oh, no. Because n's not 5. That number is 5, but n's not 5. N's actually 4. N would be 5 if I included this 8. Fuck it, let's just do it. Let's just include the 8. Right, so n is 5, minus 2 is 3. Here, we move this. Now n is 2. We move this. Now n is 1. Now that n is 1, it looks at 3 and 5, and it adds it. It looks at prev, and it adds it. And that's the whole thing. So I should have done this and just moved it. But, this is what it is. This is prev, this is prev, and I'm just moving it, right? So prev, and I'm moving this up. Anyway, and let's just see if it works. So I'm returning go. Well, I'm not returning it, so it's definitely not going to work. So let's run this, see what happens. Oh, right. So if you're going to declare a variable inside of a function, you have to make sure to make that variable available. Optionally, you can, pass it into I guess you can technically pass it in to the function. Get rid of these. Prev starts at 1. Prev starts at 2. And that avoids a global scoped variable. So I don't remember how fast the other one was, but let's just see if this works. All right, so a lot less memory because we're not doing that recursive stack. So that's good. And then let's just look at the other one. So this one is 40, so runtime was 36 milliseconds. It's just such a small runtime that it's hard to tell. And this is 30. Awesome. Thank you so much for sticking with me and sitting through this logic. This is a way you can approach any dynamic programming problem that is tree-based. And many are, but this one's very clearly tree-based, right? If you just think of the branching condition and then the branches that you can take, and then how that is a subproblem in these larger ones, right? Then it becomes very clear that this is dynamic programming problem, right? So if I made this green here, okay, the other one's already green. If I made this magenta, then I can see this as a problem, a subproblem here. What layer am I in? Okay. And even this is a subproblem, right? This one right here is actually a subproblem. So it becomes super boom, it becomes super clear that these are, makeups of the same thing. Anyway, thank you so much for sitting through that last piece. It was a lot of exploration for me, and I hope you got something out of this as well.